Okay, so for the first one, what was the function? Well, we had y is equal to x to the 4 minus 4x cubed. That was the function. So we're going to determine the integrals of concavity. We're going to start by finding the second derivative, right? And in order to do that, we got to find the first derivative. So do the power rule on each term, and you're going to get 4x cubed minus 12x squared. That's what you end up getting. All right, well now to get the second derivative, take the derivative again. And do the power rule one term at a time, and you're going to end up getting 12x squared minus 24x. Okay, and that's a polynomial, and it's got a common factor. Both of those terms have a common factor of 12x. So we could write this as 12x times x minus 2. All right, well, that's going to allow us to find the points that we're interested in. We're going to check two things. First, check when y double prime is equal to 0. When will that happen? Well, it's factored. It's two factors. So 12x will be 0 when x is equal to 0. And x minus 2 will be equal to 0 when x is equal to 2. Right? So your two values that you care about are 0 and 2. Okay, so let's make a note of that. Those values will be important. And then what else do we have to check? We want to check when is y double prime undefined. Well, y double prime is a polynomial. It's defined everywhere, right? So that's never going to be an issue, so we can say that this never happens. Okay, so those are the values that we're going to use to set up our second derivative table. So we'll set it up as follows. So because our second derivative was factored in this way, we can go back to our strategy of listing each of these factors, giving them each of their own row. So let's say that this one can be the 2x. And I could have just put x, but I guess that should have been a 12. But the point is, I didn't need to put 12x, right? I could have just put x, because multiplication by 12 is not going to change the sign of the result. But nonetheless, I just put 12x, so nothing wrong with that either. X minus 2, that's the other factor. And then we need at least two more rows, one for y double prime, and then one for the function y, one for the actual function. Okay, so, and then we're going to do slices down here once for each of these values. So we get one slice for 0, and then one slice for 2. And then now we'll go ahead and we'll pick some sample points in each of those regions. So -1 over here. I have an old habit of circling these, but since I have a different color, I don't need to circle them. So I don't know why I did that, but it's not an issue, so I'm not going to worry about it now. A number between 0 and 2, how about 1? And then a number between, greater than 2, just pick 3, how about? And like I said, nothing special about that number. I just circled it. It's an old habit. I've been trying to break it, but I failed in this case. So that's just another one of the sample points. It's just a coincidence that, or a fluke that it got circled. Nothing special about that. Okay, and if you plug -1 into both of these factors, well, for 12x, you're going to get -12, which is negative. And if you plug -1 into x minus 2, you're going to get a negative as well, because it'll be -3. So the product of two negatives will be a positive. And, well, what does that say about the function? That means the function is concave up. All right, now plug 1 in to those factors. Plug in 1 for 12x. Plug in 1 for x, and you're going to get positive 12, which is all we care about is positive. Plug 1 in for x minus 2, and it'll still be negative. So you've got a positive times a negative, and you're going to end up with a concave down function on the interval of points between 0 and 2. Now let's plug in 3. So plug in 3. 12 times 3 is positive. 3 minus 2 is also positive. So the product of those two factors is positive, and then therefore the function will be concave up. Are there going to be any inflection points? Yes. 0 is the location of a concavity change, and 0 is in the domain of this function. So that is going to give us an inflection point. Same with 2, because there's a concavity change here as well. It goes from concave down to concave up. So 2 is an inflection point, or the location of an inflection point, because it's in the domain of the function. So let's find the y values of those points, because we're going to need to give those as part of our answer. So let's evaluate the function y when x is equal to 0. So just for plugging 0 in for x here, you're going to get 0 to the power 4 minus 4 times 0 cubed, and that just works out to be 0, right? Plug in 2. Work out the value of y when x is equal to 2. And you're going to get 2 to the power 4 minus 4 times 2 cubed. So that's going to work out to being 16 minus 32, which is really negative 16. So those are going to be the y coordinates of the inflection points. And now we're ready to just summarize everything. We're ready to give our answer. So let's start with the concavity. So y is concave up on, well, 2 intervals. Let's just write it like this: negative infinity to 0 unioned with 2 to infinity. Right, so this interval here, which is all the numbers less than 0, that's this interval. And then this region here, all the numbers that are greater than 2, that's this interval here. So that's the place where it's concave up, and it's concave down in between 0 and 2. So on the interval 0 to 2. And then inflection points, let's list those. Well, we've got one at 0, and the y coordinate that corresponded to that point was 0, so we're going to have the point 0, 0. And the other inflection point has an x coordinate of 2 and a y coordinate of 16, so we'll have 2, negative 16. And finally, that is your answer. So that's all the intervals of concavity as well as the inflection points. We found absolutely everything. Okay, so that's part A. Now let's do part B. So for part B, the function was, this is the first time we have one that's not just simply a bunch of powers of x. So f of x was equal to x squared, which is a power of x, but it's multiplied by the natural exponential function, e to the x. So what now? Well, we need the second derivative. It's the very first thing you need to investigate concavity. So in order to do that, we're going to have to find the first derivative first. And that's going to be a product rule. X squared is one of your factors, and e to the x is your other factor. So if you do the product rule here, you're going to get 2x for the derivative of the first factor, multiplied by e to the x, which is the second factor unchanged. Now for the second term, we're going to leave the first factor alone, x squared, and then differentiate the second factor, e to the x, but the derivative of e to the x is just e to the x. So that is your first derivative. That's what you'll get if you apply the product rule. But now, to find the derivative of f double prime, or pardon me, to find f double prime, which is the derivative of f prime of x, we'll just differentiate this, which now we have two product rules, one here, and then another one here. But you can save yourself a little bit of effort if you notice that this second term is exactly f of x, right? So we've already differentiated this. We know when it comes time to differentiate x squared e to the x with the product rule, we know we're going to get all of this as the result. So really, we just need to do the product rule on this piece. So the derivative of 2x e to the x, let's just treat the 2x as the first factor and e to the x as the second factor. So f double prime, we're going to get 2 times e to the x. So that's differentiating the 2x, but leaving the e to the x alone. And then for the second term, we're going to have 2x, leave the first factor alone, but then differentiate the second factor, e to the x. Well, the derivative of e to the x is just e to the x, so we're going to get that. This is the derivative of the first term of f prime of x. But now to differentiate x squared e to the x, like I said, we just did that because that's f of x. So what we put here is just going to be exactly f prime of x. So we'll have plus 2x e to the x plus x squared e to the x. So that is our f double prime. And it turns out you can actually clean this up a little bit. I'm going to first of all factor out an e to the x. So we'll get e to the x times 2 plus 2x plus 2x plus x squared. Now, if I clean up the stuff inside the brackets, collect the like terms, you have 4x here, right? Combine these and you get 4x. But then I'll write the terms in reverse order so that they're in a more natural ordering, so that they're written with descending powers. So I'll have x squared plus 4x. Oh, this pen looks like it's out of juice.